Welcome back to part 2 of our deep dive into the Drake equation. In part 1, we covered the history, the formalism, abuses and criticisms of this formula. 60 years after its inception, the Drake equation is more relevant than ever as we reach for the stars, but it has garnered disrepute from academics fueled by its many misapplications. So let us now turn our attention to one of the biggest concerns about the Drake equation, the temporal aspect of it. The Drake equation doesn't really have a good way of dealing with time, and this comes into effect via at least 3 different ways. The first of these is probably the easiest to dismiss though. In Drake's equation, n is defined as the number of communicative civilizations now, but what about the distant past? The easiest way to get around this is probably just to say that the Drake equation applies to now and now alone. And when I say now, I really mean the current epoch, and I can be quite generous here and assume that n hasn't really changed much over the last 100 million years or so. After all, the galaxy hardly changes on such long timescales. Okay, fine, but there's actually a second way in which time can creep in here, and that's to think about much shorter timescales. Okay, sure, over 100 million years the galaxy hardly changes, but how can it be that the number of civilizations right now, let's say it was 1754, is exactly the same number as it was, say, 1 million years ago? Surely civilizations come and go, rise and fall. There should be some fluctuation in that number. But if one naively plugs numbers into the Drake equation, you get the same number out every time, and so this sort of implies that it's a fixed constant value. What we are really saying here is that n should be stochastic. A stochastic process is one which experiences random variations in time, like the number of raindrops splashing into a given area each second. Over the space of, say, a few minutes, we might calculate an average rate of raindrops, but in each second, the number will fluctuate up and down a little. Whenever you have a process with a stable average rate and individual events don't influence each other, then we can say that the events must follow a Poisson process. Now, in the case of civilizations, if we are willing to assume that civilizations don't go stomping around the galaxy killing each other, and we limit ourselves to timescales where the galaxy doesn't change too much, then we should expect that the number of civilizations in the galaxy right now must also follow a Poisson distribution. And that's really all we have to assume to make that statement. It's an elegant, beautiful result of statistics. To make the Drake equation stochastic is actually pretty simple. It's just an issue of interpretation. I think many people assume that n equals the number of communicative civilizations in the galaxy right now, but really it's not. It's the average number over a large number of snapshots in time. The true number will sometimes be higher than the average and sometimes lower. In fact, the spread will follow a Poisson distribution. That's actually kind of amazing. Even though we don't know anything about these civilizations, we know that the distribution must follow a Poisson. In this stochastic formalism, we could think of each term of the Drake equation as being an average, so that would mean that we have the average star formation rate, the average lifetime, etc. And actually, the original formulation by Drake calls the terms exactly that. It seems that Drake actually kind of anticipated our grievances about time, because by explicitly formulating the problem in terms of averages, it is actually more rigorous than it might at first appear. Now, despite that, I do still have a personal problem with the way the Drake equation is cast, and I think the clearest example of this comes by looking at the very first term, the star formation rate. Now, we often talk about this as the most assured term, the one that we can really measure pretty well. And that's true, but my grievance here is really with the very definition of this first term, because it's defined to be the current average star formation rate. In other words, the present day value. Okay, but here's the thing. What has the present day value of star formation rate in the galaxy got to do with the rate at which civilizations are currently emerging? The current star formation rate has no business being in there. Confused? Okay, let me put it like this. If you multiply the first two terms in the Drake equation, the rate of star formation multiplied by the fraction of stars with planets, you get the rate of planet formation. That's a well-defined term. The combination has to be a rate by virtue of the units, as discussed earlier. So let's go further. What happens if you multiply the first 6 terms, basically all of them except for L? Well, then you get another rate, and that rate must correspond to the rate at which communicative civilizations are emerging in the galaxy. But the problem is that the times now don't make sense, because the present-day rate of star formation in the Milky Way has nothing to do with the rate at which civilizations like us are presently emerging in the Milky Way galaxy. Why? Because the emergence of civilizations does not happen immediately after star formation. For example, on Earth, there was a 4.6 billion year time lag, and that is a long time. Star formation rates do change over that kind of timescale. So, why are we plugging in the current rate of star formation? That doesn't make any sense. As a way of thinking about this, imagine that the present day rate of star formation went down to 0. Now, does that mean that there are 0 civilizations in the galaxy right now? No, it doesn't. And vice versa, in the early universe, the star formation rate was much higher, but that doesn't mean that the number of civilizations present was much higher. In fact, that's kind of counterintuitive given the primordial state of the universe. Now, immediately, one might think a resolution to this is simply, instead of plugging in the current rate of star formation, to plug in the rate of star formation from 4.6 billion years ago. Surely that solves it. Well, actually, now things get dicey, because how do we really know that it always takes exactly 4.6 billion years for evolution to go by? Maybe on some planets it happens quicker, and maybe on some worlds it goes slower. Yet more, different stars have different lifetimes, and they might evolve life and intelligence at different epochs. We can't simply assume the same thing for all star types. And even worse, the galactic evolution of star formation rates is different for different star types. Very quickly, we can see that the act of trying to force to jam star formation rate into the Drake equation is effectively untenable. And look, this complaint isn't just limited to star formation either. For example, take FL, which represents the fraction of habitable planets that spawn life. But if life spawns in the first few million years of a planet's lifetime versus the last few million years, well, that seems like an important detail when considering the probability of that life form then going on to evolve intelligence. And yet, it's of course completely absent in the Drake equation. So I call this the epoch problem. Each term in the Drake equation is generally assumed to be referring to the current epoch, so the current epoch of star formation rate, the current fraction of planets with life. But clearly the date, the epoch at which these events transpire is important, and that is simply not dealt with satisfactorily in the current form of the Drake equation. So the stochastic nature of n and this epoch problem both suggest that the true number of civilizations in the galaxy right now is not well described by the Drake equation, at least as it is usually stated. So let's take a breath and step back and carefully rethink this. Before I reveal that, I want to pause and just say a quick thank you to the sponsor of today's two-parter, that's CuriosityStream. Look, it can often be difficult to find the kind of thought-provoking content many of us crave on platforms like Netflix, but CuriosityStream solves exactly that, a streaming service for the curious mind, filled with documentaries and non-fiction TV shows, including many exclusives and spanning topics like history, nature, science, and technology. You can sign up with the code COOLWORLDS to get a whole year for just $14.99, so go check them out, and thank you CuriosityStream for sponsoring us today. We've heard about how the Drake equation has been criticized for having an arbitrary choice of included terms, a linear anthropocentric view of how intelligence emerges, and how the epoch of each of these terms leads to inconsistencies. Now, to me, all of these criticisms really stem from the same thing, the overly elaborate nature of the Drake equation. After all, do we really need 7 terms to describe something we don't know? It's worthwhile to remind ourselves of Occam's razor, that plurality should never be posited without necessity. Could there be a much simpler way to describe n? At its simplest level, the number of civilizations must be governed by 2 processes: birth and death. The death side of things is actually already dealt with in the Drake equation through that last term. That's how long civilizations last for. But what is the birth rate of civilizations? Well, as we alluded to earlier, if you multiply the first 6 terms together, you effectively have it. But rather than getting caught up in the epic problem of what these 6 terms really refer to, let's just group them all together as one single rate. The rate at which civilizations emerge, their birth rate. Using the Greek symbol gamma, we can then rewrite the Drake equation as n equals gamma L. As before, this is really just the average n. The n at any one snapshot in time must follow a Poisson distribution. N is now directly interpreted as a balance between birth and death processes, a bubbling, frothing foam that is ever changing, but with a long-term, stable average. Casting the equation in this way, we can see a path forward to making greater statistical interpretations. In our video about civilization longevities, we argued that L is most plausibly described by an exponential distribution. That means lots of short-lived civilizations that burn out pretty quick, and a few longer-lived ones that last the course. Exponentials like this are controlled by just a single term. That's the rate parameter. It's usually given the Greek symbol lambda. In our case, let's call it lambda L for lifetime. Lambda L is indeed intimately related to the average lifetime L, it's just 1 divided by L. Now the average birth rate, which we're calling gamma, is plausibly constant over intervals much shorter than the galaxy's lifetime. So that means it must be a Poisson distribution. Let's define that it has a rate parameter lambda c for civilization birth. So we have a Poisson distribution for births multiplied by an exponential distribution for death. Elegantly, the product of these two is another Poisson, which actually shouldn't be surprising because we've already discussed how n must be a Poisson. Going through the math, one finds that the average number of civilizations follows a Poisson distribution with the rate parameter given by the rate of birth divided by the rate of death. A birth-death balance. Now, we don't know L, the average lifetime of communicating civilizations, but we do know how long humanity has persisted for, at least so far, and I think few would claim that we're some model of sustainability. And so, I think we could probably fairly use humanity as a kind of minimum lower estimate for L. So, how long have we been a communicative civilization for? Well, honestly, that's hard to define, because although we've been throwing out radio waves for more than a century, early transmissions were weak and would be very difficult to detect. So what power level are we talking about, and at what range, at what frequency of transmission? A communicative civilization is actually kind of hard to pin down, it's a rather fuzzy concept. So instead, let's just think about civilizations as entities and forget about the communications part for now. Humanity evolved some 200,000 years ago. We started agriculture 10,000 years ago, and we entered the Industrial Revolution just 2 centuries ago. So how do we define civilization clearly makes a difference here. Just as an example, let's use the Industrial Revolution as our example, so we might guess something like 2 centuries at least for civilization lifetime. In that case, in order for there to be multiple civilizations in the galaxy right now, we require that the Milky Way, it spawns at least 1 civilization every 2 centuries, or what's that, 5 per millennium. Now, of course, this doesn't solve the Drake equation. We still have no idea what this birth rate actually is, but at least we can understand the relationship now between emergence and death much more transparently. And as already demonstrated, one can use it to make statements about the conditions necessary for being alone or not in the galaxy right now. The downside of this formalism is that we lose the organizational nature of the original formulation. So This isn't a new and improved version of the Drake equation. It's not an upgrade or a substitute. It's just a different way of thinking about the problem. One that sidesteps the issue of how to choose all of the parameters that go into it. After all, it's fairly difficult to argue with the premise that all civilizations must at some point be born and must at some point die. Finally, I want to highlight a couple of subtle consequences of this formalism that I think are important to stress. The first is that the Copernican or mediocrity principle doesn't work. This is the idea that we exist and surely we are average and typical, therefore there should be others out there. We are not special. It's an argument frequently invoked to suggest optimism about the search for life in the universe. Now, the Copernican principle really does work great for many problems in astronomy. For example, our solar system has moons, and so it's a perfectly reasonable statement to make that other systems likely have moons too. But it runs into trouble when our very existence is predicated upon the statements being made, and we can see this very clearly with the birth-death formalism. Here, the number of civilizations follows a Poisson distribution, with an average given by lambda c over lambda l, birth divided by death. At any given moment in time, the number of civilizations is constantly fluctuating. Now, it's quite possible that lambda c over lambda l could be a really small number, and so, in that case, most of the time, the number of civilizations would be 0. But critically, now and again, in rare cases, a success will pop out, kind of analogous to a quantum fluctuation from the void. Now, we exist, so we cannot, by definition, live in a time when the answer is 0. We must live in an era when there is at least one civilization. This is our conditional. It has to be true, else we wouldn't be here to talk about it. At the same time, when we invoke the Copernican principle, we are trying to assess the probability of life in the galaxy based off a single data point. That's us. And so our data here is really that at least one civilization exists in the galaxy. And so we have a rather circular situation. In fact, if we formally write this out with conditional probability theory, you can see that the probability distribution for lambda c over lambda l, given our data that we exist, is informed by the probability of there being at least one civilization, our data, given that there must be at least one civilization, our existential conditional. And of course, if that statement sounds confusing and silly, well, it is. It's a circular statement. The value of that term must simply be 1, always. And so it doesn't matter what value of lambda L over lambda C you choose, because whatever value you choose, all of them have the same probability. They all give 1 in this equation. All paths lead to Rome. And that is that we exist, regardless of how likely or unlikely that event was. That fact is indisputable. And so despite the many successes of the Copernican principle in different arenas, this is an example of where it simply fails. Let me illustrate this using an analogy with my little assistant here. Imagine I have a bag of betting chips, some of which are
green
and some of which are
black.
Let's imagine that the green chips represent an epoch of the galaxy when there's at least one civilization, whereas the black chips represent an epoch of the galaxy where there are none. Okay, so now let's go ahead and pick a random chip out of the bag and try and use that one random chip to figure out how many green chips are in the bag altogether. Okay, go ahead, assistant, pick a chip. What we got?
Black.
Oh, but black means that we have a galaxy with no one alive in it, so there's no one around to record this chip.
Oh no!
In fact, every time that we pick a black chip, we have to put it back in the bag and even forget that we ever even picked it. So let's just keep going. Let's keep picking chips. So what do you got?
Black.
Okay, put it back. Do another one.
Black.
Black again. Do another one.
Green.
Green! Great, we finally got green. That is us. Okay, so now I've got an important question. Given that we picked this green chip, and given that we had no other choice but to pick a green chip, how many green chips are in this bag? What do you think?
I don't know.
Yeah, and that's the right answer because it's impossible to tell. But that's exactly what the Copernican principle here attempts to do, and it's plainly wrong. In fact, there is absolutely no information whatsoever about how many green chips are in this bag, given that we picked a green chip, but we had no other choice but to pick a green chip. And yes, some scientists really do this, but not my scientist.
No, that would be silly.
Okay, now, all of this probably sounds rather depressing at this point, a kind of hopeless problem with which we'll never make progress. But there is one aspect to this selection bias effect that's actually useful, indeed, even profound. Consider the following scenario, that the number of civilizations is on average 3. So that would mean that sometimes there are 4 civilizations and sometimes there are 2, just due to the random stochastic nature of the problem. And those 2 possibilities are in fact approximately equally likely to emerge. But here's the thing, because 4 civilizations is twice as many as 2 civilizations, then in fact we are twice as likely to find ourselves in such a time of 4 civilizations. This is very much analogous to the probability of being born in a high population nation like, say, India versus a low population one like, say, San Marino. The profound consequence of this is that we likely live in an epoch of higher than average galactic population. Now, this doesn't mean that the galaxy is indeed crowded, but it does shift the dial, shift the needle a little bit in our favor. And hey, for optimists like us, we need every little bit we can get. The final thing I want to address, the proverbial elephant in the room, is whether the Drake equation is actually useful. Now, to me, the answer to this depends on what you're using it for. As a direct calculator for plugging in numbers and getting anything sensible back out, I think it fails. As an organizational principle, I think the Drake equation has clearly been successful. Case in point is NE. That's the average number of habitable planets around each star. Now, for the last decade, NASA and other organizations have singled this term out as one of their primary objectives for new exoplanet missions. The Kepler telescope, for example, put that front and center as its goal. Now, that's not just because of the Drake equation, but the equation does give scientists a simple, clear way to talk to politicians and fundraisers about this series of consecutive objectives we need to address in order to reach our ultimate goal: contact. And right now, NASA and others are casting their gaze to the next term, FL, planning future missions that can search for biosignatures. In many ways, the equation has become a roadmap. Going further, I think the Drake equation, and certainly in its birth-death formalism, is a useful way to ask statistical questions about what does it take for the galaxy to have no one in it or lots of civilizations in it. It provides a framework for thinking about that problem. This isn't usefulness in the bread on the table, industrial sense of other scientific developments, no, but insights like the ways in which selection bias interacts with the formula help keep our feet on the ground when we look out to the stars and search for life. Ultimately, perhaps the greatest gift of the Drake equation is that you are watching this video, that you and others are thinking about your place in the universe and trying to come to grips with what these terms really mean. Many a night I've spent staring up at the sky, meditating on such questions, and even if its use were limited to just pedagogical means, I think it would still be an extraordinary success. So despite the criticisms, the reformulations, the doubts, and the concerns, I want to say thank you, Frank Drake, for providing us with this formula, something which has captivated many of us and will surely continue to do so. So, until the next video, stay thoughtful and stay curious. Thank you so much for watching, everybody. I just want to take a quick moment to thank our latest supporter, that is Jason Rocket. Thank you so much for your support, Jason. If you too want to support the Cool Worlds Lab, then be sure to click the link down below, and then you too can find your name shout out on here in the acknowledgements of our paper, as well as joining the live stream and the Discord for the Cool Worlds Lab. So be sure to check that out, and thank you again.